All right, so this is the second module of kernelized SVM in lecture 21 of section 4. And in this module, we will focus on carefully define what is the kernel trick of SVM. Let's get started.
So the next thing we're going to talk about is how do this phyx even related to the SVM optimization, right? My SVM optimization is minimize the margin subject to every point is predicted correctly. There's nothing really about that phi at all, right? Or how do you use the kernel? You told me, I mean, you don't need to have explicit phyx, you only need the k. But how do you use the K in the optimization, in the training, and use the testing? So this is actually very complicated. It's related to the representation, related to the scoring of SVM formulation. It's also related to what do we mean models for SVM. So next class, I'm going to talk about this much more clearly. So today is just a quick intro. How do the kernel even related to the training objective function? So this is the review. What we had is minimizing the W transpose W subject to all the training points are predicted correctly, and then it's summarizing into really just summation of all the elements take square of the W, and then subject to that formulation we had. So this is the objective function, right? If I want to change x to phyx, it looks like the only strategy I can use is to replace the x here into phi, right? Because that's the only place x is even used. Since only strategy is to change xi to phi xi. This is the training because I want to optimize to get W and B, right? That's my state of training to fit the parameters. However, the SVM uses something called dual representation of that quadratic programming. Instead of encoding the classification rules, and we're going to use something called Lagrangian multiplier, and to encode those correct classification constraints as part of object optimization formulation. So let's go back to see. So this is my objective function, or maybe it's still equivalent to 1/2 W transpose W. So I maximize the margin at the same time to require my parameter make sure all the training labels, all the training points I predicted correctly. So this Lagrangian multiplier, so if you learned about numerical optimization, this is a very generic trick. I converted the constraint into part of the scoring function. So I converted my objective function as, again, 1/2 W transpose W. This is the same way. Yeah, it's a little bit different from our way, but let me. And minus something called alpha I. Alpha I is the Lagrangian multiplier. I have a total of, let's go back to this formulation we said. How many constraints do we have? We have n training data, then we have n constraints. For each constraint, I'm using a weight function, a weight scalar, trying to weight that constraint by adding it into the objective function. So for each constraint, I create a parameter called alpha I, and then multiply yi times, this is the prediction function. So I want this together to be larger or equivalent to 1, right? So this together larger or equivalent to 1 minus the 1. So it should be positive. And all the alpha I, it's what you pick. It's called Lagrangian multiplier. They should all larger or equal to 0. So what can you tell me? What is this? I have a non-negative weight combining all the constraints and then make them part of the scoring function. If this smaller than 1, what it gives me, if this part will any of our training data, this part instead of larger than 1, it actually violating my requirement to be smaller than 1. Then this part is minus. When this part is minus, this is positive numbers, right? Positive values. This part is what? This is positive, and this is what? This is the whole scoring function I'm trying to. So let's go back to, I'm trying to minimize, right? I'm trying to minimize this part. I'm trying to minimize the W transpose W. At the same time, minimize this, right? Because I'm pushing this to be positive. If this is negative, this is not minimized. So this is a weighted summation of my margin goal and my classification goal together into one shared scoring function. Questions about this? If you learned about numerical optimization, you should learn this in the basic form. How do you add constraints into the scoring function? Sure. In this case, because there are different constraints, there are totally n different constraints. They're not the same constraint. So you have to have different weights to show how much that trade-off contributing into the scoring function. And this is actually a parameter to learn. So there are a lot of things actually to be sure.
If the y-WTX plus b value is greater than 1, then that whole part starts going, that goes positive, so
Yeah,
again,
then this is negative. This is because there's a minus here, and this is negative, this is good, right?
So,
and if this is smaller than 1.
Yeah, so that contributes to minimization when it's satisfied value.
Yeah.
Can you over-satisfy? Can you essentially create a model that's so warped at certain points that it doesn't produce the best model but produces the minimization there?
So if I can paraphrase what your question is, you mean this is too large?
Yeah, so essentially when it's...
Oh, I see. This is dominating over this, right? Good question. So this is the basic form. We haven't talked about there's actually a parameter here called C that controls how much you care about misclassification versus how much you care about the margin. That's exactly that C parameter controls. And this is which is next class. And this is just the basic form because there are already so many more you added there. All right?
So will not the alpha control the same thing? I mean, if it is very large and alpha will be so small that.
Yes, but there's a global parameter too. There's a global parameter actually controls how much you care the summation of the misclassification versus the margin. Yeah, that's the next class because there are too many concepts introduced once, so I'm introduce one at a time. This time it's the alpha called the Lagrangian multiplier or alpha sub I. It had so for every training data, there's alpha I. Every training sample. All right, this is so complicated, right? it's even more complicated. It's something you have to derive because besides the W and B parameter, now you also need to look for alpha parameter. So now you need to look for W and B best fit the data. At the same time, also the alpha sub I control that balance of my data point, my current data points misclassification contributes to the whole misclassification. How did they penalize? This is a huge, there's so many parameters. And then there are a lot of ways to do this. You convert this summation, this summarized new weighted summation, consider both the constraint and the object, the margin objective function, and you try to, don't worry about all the steps, but if you can read it, but if you cannot, in the end, you can convert the formulation into not about W and B at all. It's only about alpha. And this is called a dual form. And actually, it's, if you have some kind of numerical optimization background, it's not that hard. You try to, in the end, it's the whole idea still is that loss function versus the W to be 0. Hopefully, this is the best W. That loss function versus the B to get it, the gradient, set it to 0, it gets the B. So these two formula converted into W can be reformulated into a formulation related only to alpha, yi, and xi. Alpha I, yi, and xi, and also the same thing you can derive. B can be derived through analytic equations related to alpha, x, and y. And then you substitute the W and the B into the loss function, the whole loss function, and this is a new objective function you get. And this is actually the basic SVM loss, the scoring function. It's a little complicated, I understand it, and then, so look at this, right? And this is my revised formulation, and instead of minimize, my older goal is to minimize in versus WB, right? Now I maximize, and there's a reason why I maximize. I'm going to talk about it next time. So just memorizing for now. So now I'm trying to maximize this newly formulated dual form of objective function. At the same time, satisfies constraints actually required through the W and B derivation. First of all the alpha I need to larger or equivalent to 0, and summation alpha I, yi equals to 0. And this is actually a very, very strong constraint, which gives very good properties to SVM training and testing. And because of this formulation, so now let's see this formulation. What is it? So this revised formulation is, I'm trying to maximize in terms of the alpha now. So there are actually n, alpha 1, alpha 2, until alpha n, alpha 1, alpha 2, until alpha n, different parameters. I'm trying to learn to fit my training data. And then the whole formulation revised into this. So instead of using the phi or x, I only need to use x I transposition xj. What I only need the dot product among all the samples to learn the alpha. And then this is the training, right? During the training, I get all the alpha. So after I have all the alpha, I use the analytical form I derived. W equals summation alpha I, y, xi, and then just substitute the W into, how do you do performance and how do we predict? Our prediction is fx equals to sine function W transpose X plus B, right? And for maybe a X test. Very simple. You substitute the W into here. What you get is summation of all the alpha I that yi xi, then transposition the specific test samples, which is exactly here. Question about this? This is called the do form for linearly separable SVM. And this is the reason why kernel trick works, because we really do not need to have original phi. What we need is just X transpose X, and then if we extend it to phi, what we really need is just K, Xi, and X test, which equivalent to phi Xi transposition phi XTS. So I'm extending this linear form into nonlinear form. All right, so, and so you might be confused by here. So because I want to introduce next time. Because a very good property of this formulation, what we get, the majority of the alpha are 0. Most alpha I actually is 0. Only the support vectors, which is your margin that to boundary touches on, those points has alpha I larger than 0. There's a good reason why this is good. So because during the testing phase, this is a summation sigma alpha I over yi, then this x, the inner product formulation. If the alpha I is 0, you don't need to calculate it at all. What you need to calculate is only that kernel or this inner product values of your test sample versus the support vectors. Question about this. This is one of the good reasons that SVM, the dual formulation is better than the original formulation. All right. Okay, so now we extend it from linear to nonlinear, from X to phi X. So if you think about it, what you feed in this is the training, right? That you need to feed into your training, and so in the original X case, equivalent to you are creating a similarity matrix. The similarity matrix includes all the training data versus the other training samples, and each element is xi transposition xj. When you have this linear extension, what you're performing is a similarity matrix. Each entry is phi transposition xi times the phi xj. So this is what you, in the end, the training data provides is this matrix to this formulation, because I really do not need original phi at all. What I need is that similarity among xi and xj. It's in the form of inner product. So this is still a little bit confusing. Why does reformulation even matter, right? It's coming in the next few slides. All right, so I hope you understand from the linear to nonlinear, it's extremely simple, but just converting that X transposition Xj into phi xij and then replace it into kernel xi and xj. And then in the, sure.
Just a small question. Why was the alpha not 0 for these bounded cases? 0 for all the rest?
Oh, you mean in the training?
Yeah.
Because in the training, you don't know. You're learning the alpha through the training. You do not know which one is 0, which one is not 0. But this is actually a very good property. All this state-of-the-art optimization method makes use of the sparse pattern of alpha I to look for alpha I very quickly. This algorithm, almost all the state-of-the-art packages use something called SMO. It's exactly using this most alpha are 0 properties in the design of searching the alpha who is not 0. So you can start from everything is 0. Start from every alpha is 0. You look for those non-zeros, which is a much simple case when you start from random. Then look for who is 0. So there are a lot of tricks people use to train the SVM quickly by considering this extremely sparse pattern. SMO, actually check it out, it's a very beautifully designed algorithmic design making use of the sparse property of alpha I. All right, so this is the test page, and what you need to get is this vector of your test sample versus the training sample. But actually what you need is only the support vectors, your test sample versus the support vectors, the kernel value or the inner product values. So, sorry, there's some kind of, this is all phi. So, so why do I care about there's no phi? So there's some reasons behind is SVM is a very good tool to solve two issues simultaneously. It uses the kernel trick for efficient computation. I'm going to talk about why it's efficient. And also the dual form assigns the parameters only to the training samples, but not to the features. I'm not assigning weights to the features. I'm assigning sample the weights, the learned parameter, actually each assigned to the samples, training samples. So what is kernel trick? Why is it even efficient? The whole idea is you never represent phi. You just directly calculate k, x, and z. There are very good theorems behind something called reproducing kernel Hilbert space idea, which I'm not going to cover here. Feel free to read why this is good. And more concretely is, this is the normal kernel we normally use. Instead of define phi, we directly calculate polynomial kernels like this. So this is our polynomial kernel calculation in SVM. Instead of decomposing x into x1 quadratic or onto x1 polynomial p, forget it. I'm only doing an inner product x and z plus 1, then together take quadratic d. Why is this good? Why is this good? Instead of having this explicit each xi onto polynomial d, and then doing inner product phi x and transpose phi z, I'm just directly design the polynomial kernel, polynomial similarity as 1 plus x transposition z, and then together power of d. Why is this good? Why is this good? Yes, it's easy first, then second. Why is this good? Why is this representation good? It's an efficiency, right? Why? Think from an efficiency perspective. how many flops, how many performance computation you need if you do this. It's OP. It's an OP computation from this for performance, right? But if you decompose it, actually to explicitly write it into all the possible polynomial terms, what will be the O for this? This is OP to the D. So this basic form is only OP cost. But if you do this explicit phi x, phi z, that all the polynomial representation, then doing the inner product, this is actually cost OP to the D power. And actually you can prove this equivalent to one of this. So this is what we mean the kernel trick is an efficient way to extend into phi x representation. And there's another one much more interesting called RBF kernel, which is this form. In fact, this is extremely simple, right? It's also OP. Okay, so what is this cost? X minus z, element wise minus, then take the length quadratic, which is a computation cost of, it's still OP. There's no quadratic, whatever, at all. So this is still an OP cost. However, this kernel equivalent to, in fact, phi x is infinite size. You can't even write it's an infinite, you can actually prove it. So I'm not including that proof. Feel free to, there are actually a lot of, I can put you extra reading material about why this equivalent to phi x is infinite size. So why infinite size is good? Why infinite size of the nonlinear space I projected to is good for SVM? We just talked about it, right? Why it's good? Come on, we just learned about it. VC dimension. Whenever you have a finite size of training data, n data points, you can always linearly separate it into in the n-1 space. And this actually goes to infinite size of space, which means what? You can always, actually this kernel is a very generic kernel. You can always separate the two into your data into two cases because VC dimension is guaranteed. Question about this? And there's a reason why you like this kernel. And also, of course, it's computationally efficient. There's only OP cost.
So will this work with the lesser number of data, because in previous like regressions or so we require n to be greater than p, and here p is greater than n, that is number of samples.
Oh, you mean high dimensional case?
Yeah.
Can you rephrase the question again?
I'm just asking that in previous this regressions and so on, so we require n to be greater than p, right?
Oh, you mean, yeah, just to paraphrase the question is, in the linear regression, we want to have, because the inverse, right, that's really because of the rank of that matrix X transposition X. If you want to have the inverse, the rank should be full rank. So you have to, the P larger than case guarantees that matrix cannot be inverted. In this case, no, it's not relevant. So that type of theorem, P versus N, it's a different, so we can use that type of derivation here because it's not about rank, at least for now. So this actually needs a very, very totally different type of analysis to prove what's the minimum of N, which I'm not going to cover here. And there's a reading material about, that's more like asymptotic behavior. How many n are necessary for me to help me learn a good classifier? All right, so we don't specifically compute it implicitly because the computational efficiency, and also because for some kernels you can't even have the phi-x explicit at all. So now let me give you very concrete cases about this 1 plus x quadratic z, the polynomial kernel. In fact, the polynomial kernel matches to the phi-x, have all the elements like this: 1, x1 term, linear term, and quadratic term, pairwise interaction term, until actually really, really long. And you can prove it for the polynomial 2 case. So in this case, we have 2 features. We have, let's just prove how do you get it. You can decompose your phi-x into 1 x1 term, linear term, quadratic term, and then interaction term. And this is the x phi-x, this is the phi z, and then you do phi-x transpose phi z, you can get exactly this equivalent to 1 plus x1 z1 plus x2 z2 quadratic, which is this transposition phi-x, which is exactly this, and they equivalent to each other. But in fact, what you truly did derivation is 1 plus x1 z1 plus x2 z2. This is only cause OP, which is 2 computation, right? So I'm actually because that the one plus it's a constant computation. It's not increases with the number of features. So that's why I'm saying this cost is OP. I hope you understand what I'm trying to say here. Because plus 1 is a constant cost operation, and also quadratic is also a constant cost operation. So that's why I don't have OP plus 2 here. And this is the big O definition, hopefully you still remember from the algorithm class. And this cost is OP quadratic. It's very easy to see, right? 1, 2, 3, 4, 5. It's actually, there's a constant before the P. Yeah, so in fact, there's a constant before the P quadratic, but because the big O, so I got that constant in the multiplication out, and also the plus the constant operation out too. Because plus 1 is the constant operation. Yeah, I hope you, okay? So this is very basic asymptotic analysis. All right, so in the end, to optimize in SVM, this is my SVM basic form operation, right? Observation. What I need to have is that matrix, right? The whole matrix has all this training sample versus all the other training samples. It's related to this matrix I draw right here. So this element is OP cost in the linear case. And I need to calculate all the pairwise kernel. So to calculate this matrix, what's my computational cost? Because yeah, it's there n squared, and also it's because the inner product guarantees what? When you have an inner product, it guarantees symmetric, right? So we actually talked about this many times before. That's I transposition xj equals to xj transpose xi. And this matrix is symmetric. So which makes the computation in the linear case is OP times n quadratic over 2, but because it's constant, you can actually cancel, don't show it. And in the nonlinear case, for most of the kernel we use, each this k, xi, xj cos also OP, which is the same as the linear case, OP times n quadratic over 2. So you can tell what? In SVM, when you use this kernel trick, computationally, you really don't add much. But it's extended to very nonlinear space by not requiring much of the extra computation. You already performed in your homework too. You have to extend it using that nonlinear extension function. Whenever you have the power d, you extend it from the p to the p power d. And that specific formulation will induce p power of d times n quadratic total cost. But the kernel trick guarantees you have only just OP times n quadratic, of course, over 2. I cancel that 2 out, computation costs. Question about this? All right, so you might feel weird. So I don't just write alpha I larger or equivalent to 0 in a lot of formulations. In fact, this C larger than all the alpha I is exactly the next class if it's not completely separable. If you want to allow a little bit noise in the margin region, the whole formulation, if you allow a little bit noise, the whole difference is only that C part. So this is the third reason why the dual form is such a nice form from the original form, and which we're going to cover next time. All right, just to summarize, with the original form, this is my observation. With the kernel trick, the only thing revised is from X transposition transpose Xg into K. That's the only thing differ, and it's the same computational cost. But it gives you a much better guarantee, right? Because the VC dimension, this theorem of SVM, VC dimension just guaranteed in this larger infinite phi-x space, you got better separation boundary to be able to search. It's easier to search for the linear boundaries in the phi-x space. The VC dimension guarantees you actually can solve this better when your phi-x is larger. All right, so this is the testing case. So yeah, I already talked about it. You can prove it, why this is equivalent to infinite phi size. So I'm going to skip this to the next time, skip a few slides because I thought I can finish it. Because I want to talk about the practical guide. It's for your homework. So just a little side detour. We already talked about the whole thing you need is KXZ, right? It's that similarity matrix, and which really extend SVM from the numerical type of X. So in a lot of cases, you don't even have X, right? So assuming you have when X numerical X is even not available. It's just not making sense. So it's pretty difficult to represent maybe like a graph, sequences, or all those symbolic type of data. You don't have a numerical representation. It's very difficult to come on numerical representation, but it's extremely simple to come out a similarity measure among graphs, among strings, among maybe those symbolic structures. And SVM doesn't require you to use X. It only needs the K. So this opens a whole paradigm of the potential applications of SVM, right? If you can design KXC, because it only requires these pairwise similarities, as long as you can define who is more similar to the other. And then you can use SVM to perform principled classification. And this is really important property because I do not need to convert it into numerical X. What I need is only similarities among samples, which is for each different domain. That type of similarity is normally pretty easy. If two sequences are similar, I can use equidistance, right? I don't even need to have a representation of X, of sequence into numerical. I can use Hamming distance. I can use whatever making sense for my domain. I only need this. So which is extremely important properties that helps SVM to be applied to many real-world applications. All right.
Great. So this is the end of this module. See you in next module.